say to myself, okay, well, then I would take the derivative of this to find the velocity. And you're saying, but you're making a supposition. And I say, relax, let's just see where this goes for a minute. Let's see if this could be related to this mass on the spring. You've watched it and maybe seen it go back and forth, and it may have seemed kind of sinusoidal, but you may wonder if it fits in with all the math that we've discussed. So this is what you sometimes do in physics. You mess around. You have a sheet of paper and you just go, I got 10 minutes. I'm just going to screw around and see if this has any value. And so bear with me a minute. Hopefully in your careers you're going to have the opportunity to do this. This is how some good things are discovered, just by messing around with the equations. So I take the first derivative, and as you've told me, it'll be the minus sign. But what else do we need to throw out front to take care of the fact that the t has omega multiplying? Yeah, so we need to put omega with that. Omega a sine. So far, so good? And so I'm continuing to sit at my desk, and I'm messing around, and then I go, okay. What else might I like to calculate? I got position and velocity. Acceleration. Notice how everything this semester built upon those fundamental ideas. Position, velocity, and acceleration. And so then I go acceleration, which is dv dt. And what's the derivative of sine? Cosine. And so then we go and bring out another omega. So far, so good. Cool. So what? Well, there's a big so what. Notice you guys just told me a little bit ago that the force in this situation is minus kx. All right? And so, what else? What other force will be acting on the body in the x direction as it moves back and forth on this frictionless tabletop? What other forces will be acting on it? Weight and normal force. Okay, that's cool, but those will be in the y. And what will those do to one another? So you have the normal weight. Will they influence it as far as the motion? No, they won't matter. They'll sum up to give you 0. So there's really only one force of importance in this situation, and it's going to be due to the spring. So I'm kind of working backwards on the board today. I guess I'm in an oriental mood. Right? Working from right to left. Okay, so we're really summing forces in the x direction. What do the sum of forces give you here? Sum of forces, second law. And for this proposition, now watch this. This is one way of verifying that this would be a good guess. And when you take differential equations, you will be told good guesses are fine. All that matters is you guess something that works for the given equation. And so I've taken a guess. I said, maybe this is the x. Let's see if it works out. Here's my acceleration. So there's the acceleration, and that's a minus m omega squared a cosine of omega t. And what do we have on the left side? Minus k. And what's our x?
A cosine.
Look at this. Yeah, it's looking kind of promising, isn't it? The equality here will hold if what is true. Well, let's get rid of this because it's on both sides. Minus k is equal to minus m omega squared. Oh, so the minuses can become pluses. And therefore, omega is equal to
square root of
So let's see if we can follow this through. I watched the motion of the mass on the end of the spring. I go to my calculus text and I say, what function have I studied that kind of matches that motion? That looks pretty good. Oh, it looks somewhat sinusoidal, the motion. Let's see what happens if I would say plug it into the formula, because this is the formula that represents the situation. Newton's second law applies in this situation because we have forces acting on an object, and I know that this one works, period. So I go and say, well, if I take that guess, does it work? It works as long as what is true. This guess is going to work. It's going to provide a good solution as long as what is true. The omega, what is omega? I guess that's our next question. Well, we'll figure out what it means here in a minute. As long as this symbol omega that I've put in here is equal to the square root of k over m, then it's going to solve the problem. Now, anybody remember what omega is called? Okay, we've used angular velocity to describe this in the past. Seems a little funny to be calling it angular velocity, except for when we say to ourselves, let's consider the following. Take a ball on the end of a rod, let that angle in there be equal to omega t. So let this rod spin around a circle as time progresses. Why would I do that? What will be that length along the x-axis as a function of time? Scratch your head, think way back to chapter 1. All this ties together, and that's the reason why I keep saying, go back to those initial chapters if you're having trouble with the current material. I want to doubt if it's related to those foundational ideas. What is this length along the x-axis? Notice I'm drawing in a right triangle, so the base here is equal to cosine. Yeah, and I need one other piece of information in here yet. Before I can actually calculate that length, I need the length of your rod. And we call that length the amplitude of the oscillatory motion. Okay, well, we'll get all these definitions up here in a minute. So where does this come from? How can it be related to the angular velocity that we've introduced in the past? By putting a mass on the end of a rod and then causing that mass to spin around a circle. The position along the x-axis corresponds to what? This is turning into a weird story. That type of evaluation there corresponds to the mass on the end of a spring. If I take a mass on the end of a rod, causing it to spin about the origin in an xy coordinate system, the position with respect to the x-axis as a function of time corresponds to the mass on the end of a spring. Nifty. Now, 10 minutes, not bad. This is what you hope to have happen in your careers at some point, that you would be looking at a problem and say, it doesn't hurt to guess every once in a while. And that's what will happen sometimes with respect to differential equations. That's how some differential equations have been solved by physicists in the past. Because that's what we're actually doing here. What? Differential equation? What's he saying? Anybody know what's meant by differential equation? All of a of a sudden it seems like I started speaking French, right? And threw out a new word. It's, how did we find acceleration here? What did we do? We took one derivative, then another derivative. Some people would call that a second derivative. Another way of writing acceleration is to say the second derivative with respect to time of your position. And then on the other side, we put in our sum of forces. That's what we did in this case. This is what we mean by a differential equation. An equation that contains derivatives of a function and the original function. A differential equation. So don't think that that term really is way above you. It just means something like this. And to find a solution to a differential equation simply means either take a good guess, or sometimes you can solve the equation explicitly. You'll be able to perform some mathematical tricks. But I bet when you're taking your differential equations course here next year, you're going to see that sometimes the author just goes, here's the solution to this differential equation. You say, well, how do you get that? And if they're honest, they're going to say, somebody took a good guess at some point. And they did just what I did right here. One reason why I took this approach. Because sometimes what you're going to do is go, oh, that kind of looks like oscillatory motion. Pull it out, stick it in, and what do we see happen? The equality holds if this is so. Okay. So now, do we understand the meaning of all the terms here? K is what? Spring constant. M is? What's the meaning of the A?
R, the distance.
Amplitude.
Fail.
A is the amplitude, meaning the maximum displacement that the mass will have from the origin. That is the maximum displacement you'll see it make from some equilibrium position. So then we still have our angular velocity. Fine. Let's continue to play with this. Ian.
How does angular velocity work in this example that you have with the spring?
Okay. So, guess what? That's where I'm going next. To tell you the truth. Okay. Let's see what happens.
It's not really because you can circle on that.
So, let's answer the remaining questions that go on here. How's this actually related to the motion? Can we find the actual velocity from these? What can we do with this? Several questions, and then we're going to dive into the homework problems. So here are three very important equations. I'm going to throw one additional term into them in a minute, but I wanted to keep them simple at first. So, position as a function of time. Let's sketch out that function that I have there as far as position as a function of time. What does it look like? Cosine. Oh yeah, so A minus A, yoink. Question is, do you have that stored in your long-term memory? This is really important to say to yourselves, what's the meaning of a cosine? What does a cosine look like? It's cosine of omega t, because cosine of 0 is equal to what? 1. And then you say to yourself, okay, let's figure out some other points on this thing. Cosine of what value gives you 0? Half pi. Cosine of pi is equal to Negative. Very good. So I say to myself, this is very interesting then. So I take a look at the cosine of omega t, and I think to myself, this would be equal to 0 when omega t is equal to pi over 2. Right? That's what you guys just told me. Fine. Okay. And so then we say to ourselves, scratch, scratch, scratch. What do we call the time required to go through one complete oscillation? You remember from lab? What do we call that time required to go through one oscillation? Very good, the period. How do we symbolize the period? T. See how much you guys have learned this semester? Okay. So what? Well, there's some big so what here. Here's a general idea, and then we say, notice we know something about time in this, and that's related to the period. So, if for this to go through one complete oscillation, when the time is equal to t, we will have gone through what? So this corresponds to pi over 2, this corresponds to pi, this corresponds to 3 pi over 2, and this corresponds to. So when you go through one period, omega times t should be equal to 2 pi. Oh. What is omega equal to? Scratch, 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 another piece of information. Kind of fun what you can do just messing around. I encourage you to play with this too. Physics is supposed to be fun. It's supposed to be a discovery. You can discover a lot of these things on your own just by using knowledge you had in the past. So indeed, notice another way of expressing omega will be 2 pi over t. So consequently, when I look at this right here, when I'm looking at that point right there, and you'll have to excuse a little bit of my mess. So I'm looking at that point right there, and we said omega t is equal to pi over 2. But notice what we just discovered omega to be equal to. And I'm about ready to do my victory dance. So the time at that position right there will be multiply both sides by capital T. Divide both sides by 2 pi. Do you see it? 1/4 of the period. Oh, probably would have guessed that anyway, because we said that this time right there would be t. So this has to be 1/4 t. And what's this time right here? T over 2. This 3t. And then finally t. Cool. Questions? 1/4, 1/2, 3/4, 1 period. So, it's going through an oscillation. You can do that for the remainder of the points. Okay? We're discovering a lot. Let's continue on.